All right, so now we're going to move into maxima and minima based off of us using functions of several variables and partial derivatives. So if we think back to when we did relative max and min with a single variable we talked about on an interval. Well, now we got to talk about a region because technically we're in 3D. So a function f of xy of two variables has a relative maximum at ab if f of xy is less than or equal to f of ab for all points in a rectangular region containing a and b, or the point AB. It has a relative minimum at AB if f of xy greater than or equal to f of AB for all points in a rectangular region containing AB. So like I said, we're trying to do it in a rectangular region instead of just in an interval, because interval is for x values. So this is for x and y, so it's got to be a region. So our D test, this is the test we're going to have to use every time in order to figure out if we have maximum minimum values. First thing, we need to find all of our first and second order derivatives. So fx, fy, fxx, fyy, and fxy. Next, we're probably going to have to solve a system of equations in a lot of cases for fx equals 0 and fy equals 0 to determine our point AB. In other words, that's our critical point in terms of 3D here. Next, we're going to evaluate D. This is going to be our function that we're going to have to use every single time here. It's kind of hidden, but this is what we have to use. D equals fxx at our point AB times fyy at our point AB minus fxy at AB all squared. Once we figure out the value of D, we got four possibilities. F has a relative maximum at AB if D is greater than 0 and fxx at AB is less than 0. F has a relative minimum at AB if D is greater than 0 and fxx at AB is greater than 0. F has neither a maximum nor a minimum at AB if D is less than 0. The function will have what we call as a saddle point at AB. If D equals 0, the test is inconclusive. So we got to be aware about that we can get inconclusive testing inside of this as well. So we're told, find the relative maximum or minimum values of f of xy equals x squared plus xy plus y squared minus 3x. So the first thing we need to find is we need to find all of our partials. So f sub x is going to be 2x plus y minus 3. fxx is going to be 2. If we go fx then y, it's going to be 1. If we go to f sub y first, that's going to be x plus 2y. fyy is going to be 2. So if we notice in this case, since fxx is 2, which is greater than 0, if we go back to our previous slide for a minute, fxx is greater than 0, the only case that we can be in is that we can have a relative minimum. So the next step is we have to take our first partial derivatives, fx equal to 0 and fy equal to 0. So we have 2x plus y minus 3 equals 0 and x plus 2y equals 0. So you can solve this by systems of equations. In this case, the easiest way is going to be substitution. So if we take this second equation, x plus 2y equals 0, and solve for x, so x equals minus 2y. We are then going to take this x equals minus 2y and plug it into the other one for substitution to solve for one variable. So 2 times negative 2y plus y minus 3 equals 0. So minus 4y plus y minus 3 equals 0. Combining like terms and adding 3 across at the same time, we get minus 3y equals 3. So y equals negative 1. Since we then know what y equals, we could then plug it back in up here, which we'll see at the top of the next slide, that we will have the point 2 comma negative 1. Because when we plug negative 1 back in up here to x equals negative 2y, negative 2 times negative 1 gives us a positive 2 for x. that we were plugging in for y. So thus 2, -1 is our only critical point. So by those same partial derivatives we found 2 slides back, we now want to plug into our d function, fxx times fyy minus fxy all squared. So when we plug in fxx, so let's add in a little bit extra information here. So fxxx, so this piece is 2. Fyy is also 2 because they are constant functions. Fxy is going to be 1. So we end up with 4 minus 1, which is 3. So in this case, d was greater than 0. Fxx is greater than 0. So we will have a relative minimum. So it's a relative minimum. To find the value of the relative minimum, we have to take our point that we found and plug it back into the original function. So by plugging into the original function of x squared plus 2y plus y squared minus 3x, we end up with 2 squared plus 2 times -1 plus -1 all squared minus 3 times 2. So we get 4 minus 2 plus 1 minus 6. And we end up with -3 as our relative minimum value for this function. It's the same exact process over and over again. It's just a matter of what function we're given. Sometimes it gets a little more difficult and everything. So like notice on this case, fxy equals xy minus x cubed minus y squared. So we found all of our partials. So we end up with y minus 3x squared. And then we end up for fy, we get x minus 2y. Fxx is minus 6x. Fyy is minus 2. Fxy is equal to 1. So by the same exact theory of systems of equations, y minus 3x squared equals 0, x equals 2y. Only reason that I chose y equals 3x squared to plug in that one is because that way when I substitute in, I don't have to raise it to a power.